Related to what we're talking about right now. So, how is Madeline's 1 and 2/16 panning out? Let me just pause it here for a second. How's 1 and 2/16? We've seen 74 occurrences of 3 5s out of 16,335. What is 74 out of 16,335? 16,335. I get that to be about 0.0045. That's what that, if I do 70, what the hell's doing right here? Equals 74. Ooh, hang on. Oh, I shouldn't mess with that. Hang on. That's where all my good stuff happens. Gotta make sure oh God. I gotta make sure I hit all my phasing computations down here. I gotta make sure I don't overwrite those. So I'll put them over here. So if I do equals that number divided by that number, I get not 0. It's very small. It's that. Now Madeline's prediction was 1 divided by 2/16, right? I like the. I can't whistle, but I like that very much. Very, very good. Now it's going to be changing, yes? As we hold down F9, that number is going to be changing, but it's also going to be honing in very, very closely to Madeline's computation. Very, very nice, friends. Very, very nice. So now the question is, how about the other numbers? Are the other numbers believable? First of all, is this the kind of shape you would have expected if this is a Vegas game? Because where are the big payouts? From the player's perspective, where are the big payouts? The big payouts are here, yes? And I say big. This one you win $1. This one you win 9. But these are the payouts. These are the positive payouts. And they also correspond to the smallest probabilities. What's the best payout for Vegas? 0. Which has 58% probability, which is what this says. The break-even probability, which neither you nor Vegas win, has a 34.3% probability. So that means combined total, putting those two together, you got about a 93% chance of either losing money or breaking even, which Vegas loves an awful lot, yes? Keeps you playing the game. And then they have this beautiful chance of, what if I win? What if I win? Well, yeah, what if? 7 times out of 100. There you go. But the problem is, in 7 times out of 100 you've won, all the losses you had in the 93 times out of 100 don't offset the 7 out of 100 to which you won it back. More on that later. Fair? So where do these other numbers come from, do you think? This was 1 and 2/16. So how about this one? How many outcomes out of 2/16 is this? This is not getting any 5s at all. So using Madeline's idea from she did 1/6 times 1/6 times 1/6. What would this actually be? What times what times what do you think? What do you think? You might not be able to do this right now, and it's okay. We'll hit it again next week with chickens, with the context of chickens. But, well, you don't want to roll any 5s, yeah? So you got a die and you're throwing it. How many ways can that not be a 5?
5 times 5 times 5.
Yes! It's 5 times 5 times 5, isn't it? Because you want to roll either a 1, a 2, a 3, a 4, or a 6 on each of the 3 dice. So you've got a 5/6 chance on the first die of not getting a 5. You've got a 5/6 chance on the next die of not getting a 5, and a 5/6 chance on the third die of not getting a 5. So this should be 125, 5 times 5 times 5, divided by 2/16. And how close is it? Well, I don't know. Let's see. Equals 5 times 5 times 5 divided by 6 times 6 times 6. 57.87? It's damn close. It's damn close. Now it gets more interesting in the middle two. Because in the middle two, you have to get some 5s and some not 5s. So you're going to have to mix and match 5/6 and 1/6. The 1/6 would be getting a 5, the 5/6 would be not getting a 5. Then you have to worry about where they are. Let's deal with that next week if it's okay with you guys. Because, oh, Tony, what's on your mind? You thinking about something? I'm sorry, I see motion again. Zach?
I was thinking like if you get a 2 and a 3, it's a 5, but it's...
Oh, it's not a sum, correct. It's not a sum of 5 like craps is. You have to actually see the 5 pips on one die to win this game. Yeah. There are other ways to bet too, but this is the most simplistic betting scheme. Yeah, so you're not summing up to get a 5. So yeah, like a 1, oh, that got really weird. Pull the die this way. So yeah, you can't like 1 plus 4 doesn't make a 5, unfortunately not in this game. That'd be a fun game to design though. Many ways you can get the sum of 5 or a 5. Ooh. Somebody do that. Let's go to Vegas and make a lot of money together. Come on now, new game. We'll call it whatever you guys want to call it. But anyway, so now my question. stabilized pretty well, haven't they? They've stabilized fairly. We can hold that F9 a little bit longer if you guys want to. But what you're noticing over there is those numbers are pretty much stabilizing where they need to be. I mean, they're changing a smidge, but I think they're close enough to call them done. So, if you were Vegas and you needed to know what average gain or loss was being made on this game, could you now figure it out? I think we can. I think we can. We got everything we need. Vegas, by the way, does stuff similar to this all the time with their games, constantly. When new games come along, they have to model them mathematically to see what's going on. And with old games, they know the numbers. So, pretty fun. So, what's the chance of losing $1 as the player? We're going to call that 0.5809. And Cody, we're going to deal with all that precision issue right now, too. The only precision is going to happen probably way out right in the last two places. We'll leave it in just to be consistent. 3430. 34.3%, so roughly 1 in 3 games you win your dollar back. Roughly 1 in 3 games. That's mentally very, very good for Vegas. Because 1 in 3 games, you're being handed $1 back. Think about that. You're getting something back. It's like a placebo effect. They're handing you money, and you're like, ooh, I'm getting money handed to me. Yes, they're giving you back the money you just gave them. But that's not how our brain processes it. It processes that they're giving you money. $1 win, about 7.16% of the time. And then finally, 0.0045. 0.0045. Just under 0.5% is the big win. Big win. So what is that? 1 every 216 trials. There we go. Beautiful. All right, friends. What's the average? Go get it. Go get it. Go give me the average. Go give me the average. I'm going to do it by hand up here while you guys are crunching it by mechanics. Because I want you to kind of understand where $1 goes in this game. The average. Expected return. It's -1 times that. Plus 0 times that. Plus 1 times that. Plus 9 times that. That cancels. That's going to be about negative. I want to guess it's about negative 50. Is it close-ish? What do you guys get? Let's get more precision.
Negative 0.4688.
I'm going to call that 47 is okay here. Just round it off to make it like, because we often don't talk about hundreds of cents and tenths of cents. I guess it'll be about negative 50 cents. Aaron's giving me a more precise answer of negative 0.47. So in other words, we just found a guaranteed way of turning $1 into 50 cents, didn't we, on average over time? We just found out that every time you walk up to this table and lay $1 down, on average, Vegas takes half of it away from you. That's what the negative means, right? The negative is a loss on your part. You can ignore the standard deviation. Can you see why we're ignoring the standard deviation of this distribution? This distribution is highly, highly, highly skewed. Ignore the standard deviation. It's not what we're talking about. But the average is important, because the average is going to happen on average over time. Think about casino. Think about how busy casinos are. Hundreds of players playing every moment in any given casino. Thousands and tens of thousands over the course of Las Vegas or other gambling cities. So the average is worth talking about, because Vegas knows every time somebody walks up and hands them $1, it's basically they're giving them 50 cents for the privilege of watching the birdcage go around one time and drop dice. Now you got to realize that some of those times Vegas has to pay out $9, right? That's included in that average. Because you have to realize, and this is why I wrote these 4 components down, friends. Follow the dollar, right? Follow the dollar. 58% of the time you lose the dollar. So that component of the average is negative 58 cents. You're already in the hole right there. That's negative 58 cents. The other 3 components are digging you back out of the hole. Digging you back out of the hole. This doesn't do any digging whatsoever, because there's no payout. So you're still at negative 58. This does a little bit of digging, correct? does a little, this digs just 7 cents out of the hole, right? 7.16 cents times 1 is 7.16. Yeah, that's good. That's good. That digs you out 7 cents. So now you're down about negative 51. And then you're like, oh, but this $9 over here, that digs me out. Yes, that's $9 times that, which is less than a half of 1%. So that doesn't do very much digging. It is positive. It's just barely positive. And Vegas knows that. Vegas knows that. So suppose they go, okay, Chuck-a-Luck's down right now. Chuck-a-Luck's down. People want to play Chuck-a-Luck. Have you guys ever heard of this game before? Yes, it's that popular. Go, maybe. You've seen it. It's usually covered in dust under a staircase. Usually, from what I've noticed. I like to wander through casinos before the smoke gets to me. I like watching what people are doing. Craps is always off the hook. 5-card studs always off the hook. Give those games a chance. So suppose the casino boss is like, okay, Chuck-a-Luck's down. Chuck-a-Luck's down. Let's change the payout for 3 5s to make it more appealing. Make the slots looser. That's a phrase that was huge. So right now it's a 10-to-1 payout, yeah? It's a 10-to-1 payout. What should we make it, friends?
50.
50-to-1 payout! You ready? 50-to-1 payout! That means you get $49 for a $1 bet. Now you clear $49, right? If you bet $1 and you get 3 5s, you win 50 back, but one of those dollars you have to replenish from your own supply. What's the average now? What's the average now?
.28.
Negative?
Negative 0.28.
That's huge, isn't it? Whether the negative's
yeah,
there or not?
Yeah.
Okay, so Zach, we're going to come back to that.
You said it's huge, but it's...
Well, it's huge to have the negative there, correct?
Right.
So, you look at your average. All you got to do is change the 9 to a 49 and run the average again, yeah? So in other words, it would change this to 49. Fair? Fair-ish. Fair. So think about this again. Think about this again. You're in the hole 58 cents. You're still losing at the exact same rate. You're losing that dollar 58% of the time. You're still not winning anything back when you roll 5. And you're still clawing back out of the hole with 7 cents here. But at this point, you're at negative 51 cents. The last gasp for hope is this. And you're like, 49 bucks! Hell yeah! If I'm down negative 50 cents and I add 49 bucks to it, I'm now up at 48.50. To which you, as the statistician, go, yeah, except for the fact that 49 only happens that often. And when you weight that with that and add it to your negative 51, your average is negative 26 cents, 36 cents, whatever you guys are. It's still negative though, isn't it? It's still a negative. Vegas knows that. Which means even if they increase the payout to 50-to-1 odds from 10-to-1 odds, they're still, on average over time, going up. Make money off of you. Make money off of you. I got a quiz planned for you guys in a couple of weeks to figure out what the break-even point is for Vegas. Because they know what that is too, don't they? They know what they can set this to make it a break-even, which means the average would then go to 0. And they know not to get near that. Now they're going to, of course, if this average being 49, the average now, the new average is going to be, what you guys say, negative 28, have I heard? Yeah. 29? Yeah. So clearly, they're not making money as much as they were making it over here. But they're still making money. And the idea is, if the game was running slowly anyway, if they get more people to play, if they get more people paying a little less money, that's better than having fewer people paying a little more. Does that make sense? So it's all this game. The bosses play not the bosses, the managers of the bosses play all the time. How can we finagle the games to make them more appealing? Finagle the games to make them more appealing. Make sense? Believable? Yeah? Questions on this? Yeah. Please, Madeline, go!
So the sum in one of our stats comes out to the same as the X bar because you're dividing it by the probability of that one, right?
Yes, ma'am. Essentially, that sum is what I just did right here.
Right.
It's this guy right here. It's exactly that. It's just because it sums to 1, it's going to be the equivalent number as the average.
Okay.
It's just because the TI doesn't know you're dealing with a distribution, a probability distribution, which goes back to Sean's question you asked about 20 minutes ago. If you were to graph the frequencies as opposed to the probabilities. So in other words, if I was to graph these numbers, 9782, 5776, 1206, and 75, instead of the relative frequencies, the graph would have the exact same shape. There's no difference in the shape whatsoever. It would just be much taller on the y-axis because they're bigger numbers. But as far as the shape goes, it's exactly the same. It goes back to an old rule you learned in Math 111 about horizontal and vertical compressions. So, but the idea is, why don't we just do the frequencies? Why do we do the relative frequencies? Well, the frequencies are constantly changing up there, right? As we accumulate more data, but the relative frequencies don't, they stay constant. Which means we can then treat them like a population, which means we can just focus on the one standard deviation versus deciding which one to focus on. Fair? Good. Very good question. All right. Here's what I want you to do next. Perfect. This will take us to the end of class. I brought an in-class quiz. What does all this have to do with me dying? Well, believe it or not, everything. Well, not everything. I shouldn't say that. Not everything.